Okay, so Zlatko is listening. All right, so it's my pleasure to introduce today's speaker, who is Dries Sels. So he studied at Delft, Antwerpen, and Leuven, and then he did postdocs in Boston and Harvard. And now, or soon, will be at New York University and from what I understand, Flatiron, but I'm sure he'll correct me if I'm misunderstanding something. So Dries is going to talk to us about probing the onset of quantum chaos through eigenstate deformations. So, Dries.
Yes, exactly. Thanks, Achilles. Thanks everybody for organizing these nice seminars. It's a pleasure to give a talk. It was less early than I thought. For the longest time, I forgot that the time difference between the UK and Boston is only 5 hours and not 6 hours. So I was thinking I would have to give a seminar at 9 a.m., but it's only 10 a.m. So I'm a little bit more awake. So as advertised, I'm going to talk a bit today about two works we've recently done on detecting the onset of chaos or ergodicity through eigenstate deformations in quantum systems. And the work is in collaboration with mostly people at BU. So Mohit was a graduate student of David Campbell, and then Anatoly Polkovnikov, and then also Peter Klaas, who's now at Cambridge. Okay, and so, of course, in quantum many-body systems, we can ask generically sort of what is the dynamical behavior of a system, or what is the quantum phase of the system at infinite temperature. And if we ask about determining phases of quantum matter at infinite temperature, then roughly there's kind of two things that a system can be. It can either be ergodic or non-ergodic. And well, then there's not much more else at infinite temperature there is. And so ergodic quantum systems, we all know them. Typically, we think of them as obeying some kind of random matrix theory or eigenstate thermalization hypothesis in a more kind of refined setting. They all have universal late time dynamics, and these systems tend to thermalize. And on the other hand, on the complete opposite, we have non-ergodic quantum systems, and these non-ergodic quantum systems typically they're integrable because they have some underlying integrals of motion. If we were to do a quench under a certain Hamiltonian, these systems would retain memory of their initial state essentially forever, so they don't forget where they came from. As such, they equilibrate to a so-called generalized Gibbs ensemble, which kind of incorporates this memory of the initial state. And if we think about what observables look like, then in contrast to these ergodic quantum systems, non-ergodic quantum systems, they have very large fluctuations of the matrix elements of operators in the energy eigenbases, which translates into the fact that if we were to look at some observable at late time, then even though this observable at late time, it will equilibrate and its expectation might be described by some generalized Gibbs ensemble, there would still be very large fluctuations around this final value. Well, very, very large, meaning much larger than in the ETH case, in which case those fluctuations are exponentially small. And this, I would say, is kind of the two extremes of dynamical behavior of many-body quantum systems, or well, systems in general, I guess. And recently, there's been lots of work about what happens in between. Are there sort of in-between systems? And these in-between systems can be many things. Can be systems having so-called quantum many-body scars, which means that they are, for all practice, they're really ergodic systems, but there are some special states which do not behave, obey this ETH prediction. There's Hilbert space fragmentation and all those kinds of new concepts. But today I'm going to ask a very simple question. So it's not going to be about scars or fragmentation or anything like that. I will just ask a simple question, that is, what happens if we take an integrable quantum system and we just break its integrability. At some point, the system has to go from being non-ergodic to becoming ergodic. And how does that happen? And how do we detect it? So that's the thing. Most of the talk will be about detecting this onset of when the system goes from non-ergodic to ergodic. And the first part of the talk will be about a clean quantum system, so 1D XXZ chain, basically. And then the last part of the talk will be about disordered quantum systems, which basically many-body localized systems, which are specific non-ergodic quantum systems, and we'll see how you can go from being many-body localized to being ergodic. And there, to make the disclaimer in the beginning, I think based on these new probes, we are kind of detecting that the MBL phase might be unstable in the thermodynamic limit. And so what happens in between is indeed something very, very interesting. And in classical many-body systems, or in classical few-body systems, usually we know what happens, and there's so-called KAM theorem that basically means that there's some coexistence of chaos with still regular quasi-periodic orbits. And so the question, and I think it's one of the open questions in quantum many-body physics, that is there some kind of quantum KAM story? So I'm gonna advertise kind of the result of our discussion already in the beginning, just so it's completely clear what the story is going to be, and just if I run out of time, then everybody at least has seen it. And roughly, as I said, the story I'm going to try to present to you is the following. So we have, on the one hand, integrable quantum systems, and we have ETH type quantum systems. And now we can make a simple diagram which might consist of something like the system size on the horizontal axis, and on the vertical axis I'm putting something which I write as log of the integrability breaking perturbation strength. So you can think of this as there's some kind of perturbation on the y-axis, and there's system size on the x-axis. And so, of course, if there's no perturbation, then the system is integrable. That was our definition from the start. And then if we perturb the system, at some point we expect that the system will become kind of random matrix theory and obey eigenstate thermalization hypothesis. And that's what's happening. And if the system size becomes larger, you need a smaller integrability breaking perturbation to basically go to an ETH system. And so the result we find is that, remarkably maybe, or at least to our surprise, there's a regime in between that separates this eigenstate thermalization hypothesis system, so random matrix system, from the integrable system through a region which one might call a region of maximal chaos. So that is a region in which the system is actually much more susceptible to perturbations than a random matrix system. And so this region in between of maximal chaos, I'll explain in a second what it is, but it's the same region of maximal chaos, which we believe ultimately kind of impedes many-body localization as well. So okay, what is the probe we're gonna use today? So basically, how are we gonna probe this transition from ergodic to non-ergodic? Well, we're gonna look at the fidelity susceptibility of the system. And so what's the fidelity susceptibility? Consider you have a certain Hamiltonian H, and the Hamiltonian H depends on some parameter lambda. So it's parametrically dependent on some set of parameters lambda. So I can now define the eigenstates n as a function of lambda. That is, as a function of these Hamiltonian parameters. And now what we would like to do is deform the Hamiltonian. So that is to change lambda from a certain value to another value, lambda prime. And so what I can then define is a distance between eigenstates. And if I have only one parameter lambda, then this distance, call it say ds squared, is just 1 minus the overlap of the eigenstate n at value lambda and the eigenstate n at value lambda plus d lambda. And so if d lambda is very small, then basically I can expand it to second order and I get something of the following kind. There's some chi of n, which is exactly the fidelity susceptibility times d lambda squared. And basically what I've just written down is the diagonal part of the so-called Fubini study metric, which is the metric on eigenstates of quantum systems. And this fidelity susceptibility, it's not so hard to work out. Basically, it is the second derivative of this wave function n of lambda projected on n itself. And so now, because n was an eigenstate, you can basically just use Hellman-Feynman theorem to turn this into derivatives of the Hamiltonian. And as a consequence, you get some energy denominators. And so basically, the fidelity susceptibility is nothing but kind of the square of the correction you get in first order perturbation theory, right? It's the matrix element n d lambda h m. You square it and you divide by energy denominator squared. And okay, so now just to set some expectations, as I said, we're gonna try to use this fidelity susceptibility chi to probe whether the system is chaotic or not chaotic, right? And so, well, in order to do so, we need to set some expectations, right? What do we expect? And the reason we can do it is the following, is that basically, let's think about a random matrix system. Well, in a random matrix system, typical matrix elements between, say, a random perturbation, typical matrix elements are of order 1 over d, where d is the Hilbert space dimension, right? Well, 1 over square root d. And so basically I get 1 over square root d for these matrix elements. I square them, so I get a 1 over d. But then I get a sum over these energy denominators. And these energy denominators, well, basically that gives you the density of states itself. So basically, because of these very small denominators and because there's a square here, basically what you get is that the fidelity susceptibility for a kind of random matrix perturbation actually scales with the Hilbert space dimension d. So chi of n is proportional to d, which in a spin chain, for example, would be just 2 to the L. And so we get kind of exponentially large susceptibility for random matrix systems. And of course, that's expected because, as I was just saying, this is saying what is the overlap of an eigenstate n with an eigenstate n of lambda plus a small perturbation d lambda. And of course, it's clear if you pick an eigenstate of a many-body quantum system that's ergodic, and I would slightly change the Hamiltonian and the eigenstate is in the middle of the spectrum, yeah, even if I exponentially, I need only an exponentially small change to make the eigenstates orthogonal, right? And that's what this is saying. Okay, so this is our expectation for random matrix systems. But now it turns out that if you work out the same thing and you pick a carefully chosen perturbation d lambda h, namely in integrable systems, you pick a change of the Hamiltonian that is conserving integrability, then actually what you get is that, so in chaotic systems, this is exactly showing this fidelity susceptibility chi on a logarithmic scale as a function of system size. And so in a chaotic system, we indeed see that it scales exponentially. And it exactly scales like 2 to the L, as we expected. So the chaotic system in this specific case is just an Ising model with a longitudinal field and a transverse field. Okay, and so now if we go to the integrable system, well, let's first take the simplest thing. Let's take transverse field Ising model. So a free model, which is basically the same as the yellow curve, but we switch off the longitudinal magnetic field. Well, then if we look at the fidelity susceptibility as a function of system size, it's just a constant because the problem is just completely non-interacting. And as long as you don't do it at the critical point, this is just a constant. And so you see that you get a constant fidelity susceptibility in this free model, and you get an exponential fidelity susceptibility in the in the chaotic model. And so if you do it on an XXZ model, which would be an interacting integrable model, it's already kind of interesting that basically you get polynomial scaling for the fidelity susceptibility. So the fidelity susceptibility is a polynomial of the system size, so not an exponential. But that polynomial basically is not universal, and it depends on the anisotropy of the model. So this particular thing that's shown here is for an anisotropy delta of 1.1. And so this is the basic idea now, is that since by carefully choosing which operator the lambda h to probe, we can get polynomial scaling for the fidelity susceptibility on an integrable model, while it would be exponential in the non-integrable model. It seems like we can use this as a good detector, right? It seems like we can check by basically probing the system whether this fidelity susceptibility is still polynomial or it's already exponential. And hopefully, at least that was the hope when we started this project, is that because this change is exponential, it might be an easy thing to numerically detect, even though we only have access to small system sizes. And so that's exactly what we set out to do. So now what we're going to do is the following thing. What if we take our XXZ model and we add a small perturbation? So I've replotted exactly the same thing. So the system size L and this fidelity susceptibility chi on a log scale. And now what I'm going to do is I'm not going to study the clean XXZ model alone, but I'm going to add some integrability breaking perturbation epsilon. Now I want to see what happens if I crank up epsilon, right? And so, okay, let's do it. So basically, if I put in some very small epsilon, then at very small system sizes, the fidelity susceptibility is still exactly the same as before, right? All of the dots are exactly the same. But then at some point, for some given system size, we start to see some deviation from the perfectly integrable result. So now I can crank up epsilon a little bit more. And we see exactly the same. Again, for small system sizes, nothing happens. But now at a slightly earlier point, the susceptibility starts to deviate from the integrable result. And we can keep going. You add larger and larger perturbations. And as you can see, every time we increase the perturbation, what's happening is that basically we go to exponential scaling of the fidelity susceptibility at a smaller system size by cranking up epsilon. And so how exactly is that happening? So what we can do now is basically we can determine all these intercepts where these parallel lines where you get exponential scaling intersect with the integrable result. And then basically what we can see is, well, if we now plot the integrability breaking strength epsilon b as a function of the point where basically the lines start to deviate, that's kind of the critical perturbation that would be required to see exponential scaling of the fidelity susceptibility. And we see that this very nicely exponentially decays. And so we are detecting some exponentially decreasing threshold in the system size to start to see deviations from integrability. And the second thing—
is there analytical results for this?
No. Well, no, not. We are working on a complete kind of, I would say, RG picture of how this works. But as of now, there is no analytic result for this.
And also, are you looking at the ground state fidelity?
No, this is the infinite temperature fidelity. So if you look
Can you
at
describe
the
a little bit how you calculate this? I was going to ask the same question. Can you briefly describe how you calculate these numbers?
Exactly. So these numbers are basically computed by exactly evaluating this chi-min. So you basically do ED on a small system size. You compute chi of n for all the eigenstates n, and then you just compute the average.
So, but the lambda h, do you like create a grid of h and then literally extrapolate numerically, or do you?
No. No, the lambda h is basically that's just another operator, right? So lambda in this case, I should have been more clear. Lambda in this case, you need to pick it an integrability conserving deformation for this exact story to hold. So that basically means in this case, we're changing the anisotropy. And so lambda is the anisotropy delta. So then the lambda h is nothing but ZZ on neighbors, right? So this is just, I really compute the matrix elements of the ZZ nearest neighbor interaction between all the eigenstates n and m.
So eigenstates for a fixed epsilon.
For at fixed lambda, exactly, at fixed lambda, and in this case,
I mean
epsilon. Exactly. So you do this for every epsilon. And so that's what's shown here. So you do it for epsilon 0. That gives you the bare XXZ model. So that gives you this polynomial scaling. Now I do it not with the bare XXZ model, but at some fixed epsilon. Then I get the red line. Then I increase epsilon, right? And I increase epsilon and I increase epsilon. And then from this, what we determine is basically, well, what we observed. And so that's the lines that are plotted. What we observed is that the slopes are always the same. And so what we have done to determine these lines is to basically fit all of these curves when they intersect together. So collapse them and do one fit. And so basically that's what this line is showing. And then from that we determine the intercepts, where basically you start to deviate.
Sorry, I
from
have
the
a question.
result. Yeah.
So it's probably a stupid question, but since your perturbation is a single site operator, I would have thought that this affects the smaller sized systems first. So why does it affect the larger sized systems first?
Well, it affects the largest system sizes first because it's much easier to break integrability on a much bigger system, right? Because all the matrix elements are closer together. So if I increase the system size, my level spacing is exponentially decreasing, right? So it's much easier to mix the eigenstates in a very large system than in a very small system. But it's true that you could wonder whether somehow what I'm saying is not caused by the fact that I added a single site perturbation, right? Because the single site perturbation might somehow be very special because it's local and we have a local Hamiltonian. But that turns out not to be the case. So for example, so in the paper, you can check, it's on arXiv. We do the same thing with next nearest neighbor interactions. So that's also integrability breaking. And it looks exactly the same. The thing I'm showing here in this panel B is basically the same thing on the transverse field Ising model. So if you take the transverse field Ising model and you add a longitudinal magnetic field, that also breaks integrability. And again, you see exactly the same. The only thing that's different is that basically the integrable result, in contrast to the XXZ case, for the Ising case is just flat because it's non-interacting.
And a related question. So in the XXZ case, because it's an interacting integrable model, is there some analytic argument to believe, which will sort of compel me to believe that the black data at much larger sizes also doesn't become exponential?
Well, so we have been trying to figure it out, and it's very hard to establish. So we haven't succeeded in basically, it would seem that you could just show this from beta ansatz, but the problem is that you need to compute all matrix elements. And that's just exponentially hard, even if you have a beta ansatz integrable model. So we don't know. That's the answer.
Okay, thank you.
Yeah. Okay, and so one final thing I wanted to kind of indicate, which is important, is that okay, so we start to see that we can detect this deviation from being integrable, and that we detect it at some threshold epsilon d, which is exponentially decreasing with the system size. But kind of remarkably, if we look at these slopes, so how quickly is the fidelity susceptibility increasing with system size L for fixed epsilon? Actually, it increases roughly like 4 to the L. So in other words, it increases like the Hilbert space dimension squared, not the Hilbert space dimension, which means that this increase in the fidelity susceptibility is much faster with system size than an ETH type system would predict. Because if you have random matrix theory, then this increase as a function of L should be just exponential with an exponent 2 to the L. But now we see 4 to the L. So we get some enhanced susceptibility when we are breaking integrability. And I'll come back to that again later. So just to compare this to kind of standard measures that we all use, which is measures for kind of how well a system can be described by random matrix theory. So if we compare this to the level spacing ratio, R, for the same system, then we can make we can scan the integrability breaking perturbation epsilon d, and we can look at the level spacing ratio R. And of course, if epsilon d was 0, we should get Poisson statistics. And if epsilon d is very large, we should get Wigner-Dyson statistics. And we see indeed that it goes from Poissonian to Wigner-Dyson. And the plots I've shown you all at epsilon d's in this range, basically surround in the range of 10 to the minus 3. So that's where we start to see the onset of this exponential scaling. But it's clear that the system only becomes ergodic at much larger integrability breaking strengths. So we see the onset way before the system becomes fully ergodic. And actually, I mean, there's been a lot of work in the past by people like Lea Santos and Marcus Rigol that have tried to extract from this level spacing ratio some sort of scaling of how large an integrability breaking strength do you need, and they typically see polynomial kind of scaling, and that basically means that since we have exponential scaling here, there's still a very big kind of exponentially big range in between the regime where we detect the chaos and where we would get fully mixing or full ergodicity. And maybe one colloquial way to understand that the increase in the fidelity susceptibility goes exponentially faster than in the ETH case is because the system needs to catch up with the ETH system, right? So if I were to have a system of a certain length L, if it would be ergodic all the time, it would already have exponentially large fidelity susceptibility. So if somehow for some epsilon, the system would ever become like an ETH system, well, there needs to be a region in the middle where the fidelity susceptibility scales much faster with L than the ETH system itself, right? Otherwise, it can never go from polynomial to being exponential if it wasn't in between somewhere exponential with a higher exponent, right? That's kind of a vague way to maybe understand why this is plausible. Okay.
So looking at this plot, you would call maximally chaotic something starting at 10 to the minus 3, and then
exactly. So we start to detect it somewhere here, and it persists all the way up to, yeah. Actually, you can also see it on the ergodic side. So in this case, we're coming from the integrable side. You can also come from the ergodic side, and also on the ergodic side, you start to see, once you get close to the transition, you start to see enhancement of the susceptibility or increase of.
So the definition of this maximally chaotic thing is this susceptibility of fidelity.
Exactly. So our definition of maximal chaos here is to have a susceptibility which is scaling with the Hilbert space dimension squared and not the Hilbert space dimension. And that's actually the upper bound. So that's why we call it maximal chaos, because it's really not possible to have any exponent that's larger than that. And Well, we borrowed the terminology basically from the only case in which I know that a similar thing pops up is in these dual unitary circuits, where basically you get entanglement growth, which is at a rate which is also the square of d and not d. So basically, which people have dubbed maximally chaotic systems. So I don't know if this is a particularly good term, but physically, I think it is okay, because indeed the system, if chaos is defined through having exponentially large susceptibility, then this is much more chaotic because it has a larger exponent and it has the maximal exponent.
But this fidelity is a basis dependent quantity, right?
Yeah, so we express it in the eigenstate basis, right? So it is invariant under, I mean, it's expressed as the susceptibility of the eigenstates of the model. But the point you can make indeed is that it is dependent on which probe you're using, right? It is dependent on what was my d lambda h. And if I pick another one, I might get a different result, right?
I mean, it's expressed in terms of eigenstates, but you're comparing eigenstates at different parameters, right?
Exactly, exactly. Which is the same statement as saying that because you compare them at slightly different parameters, you have to define how you're going to deform these eigenstates. And so it's not a property of the eigenstate alone. It's basically a property of the neighborhood of the eigenstates, right? Because I need two different points. And so I need to define that problem, yes. And yeah, I mean, that's what we, I mean, that's, if you set it up like this, where basically you are deforming it along integrable directions, then you get this nice feature. If you actually deform it with a random matrix, well, then you get, then the fidelity susceptibility is exponential regardless of whether the system is integrable or not. And I wasn't going to talk about this today, but I mean, you can find it in the paper. Basically, it's still possible to distinguish integrable and non-integrable system, even if you do a random perturbation. So even if you apply a random matrix to the system, but then you can't detect it from the typical susceptibility, but you have to look into the probability distribution of the susceptibility. And basically, what you can do is, if you look into the tail of the fidelity susceptibility distribution, it will tell you whether the system is ergodic or not.
So a different way of looking at the same data would be that the perturbed integral systems have lower susceptibility than you would expect for a chaotic system.
Exactly.
So you'd be saying then that, like, why is it the change in the susceptibility with system size that you use to say like how chaotic it is, rather than how susceptible it is? Like the scaling with system size being,
well, but that's the thing, right? Then you can't. I understand, but the reason we're looking at the scaling is because, I mean, because from the scaling, you can determine something on small systems, right? I agree that you could also just look at the susceptibility itself, right? And then you would just see that, well, this system is much more susceptible than another system. But what does much more susceptible mean if you're not comparing it somehow to some expectation that the system would be exponentially susceptible or not?
But these so-called maximally chaotic systems are much less susceptible to perturbation than a system that started out chaotic.
Exactly. That already started out to be chaotic. Exactly.
So it seems
that's completely true.
Maximal.
Well, as I said, it is maximally chaotic in the sense that it saturates the upper bound of the scaling with the system size. And the reason this is, so the fidelity susceptibility is not a dimensionless quantity, right? It has a prefactor, which is, and in this case, actually the prefactor is epsilon squared, roughly. And so then you see that, yeah, of course you get much smaller susceptibility because the susceptibility of this exponentially increasing part also scales with epsilon. But if I were to normalize my susceptibility by the integrability breaking perturbation strength and divide this susceptibility by epsilon, then I would just get 4 to the L, right? So of course you're right that they are less susceptible in absolute terms than the equivalent ETH system, but it's only because basically there's a small parameter in the problem, right? And the susceptibility also scales with this small parameter because it has units.
Okay,
but I mean, I agree that I mean, we're not fixed on the nomenclature of maximal chaos. I'm very happy to call it something else because in a certain way, it's also just very weakly chaotic, right? Because as you say, it is in that sense, it is at that point still less susceptible than if it were to be a complete random matrix system. But yeah, and I think these dual unitary circuits have a very similar thing. In some sense, they have maximal chaos because they scale, they saturate the bounds of the scaling of the entanglement growth, but at the same time, they're also less chaotic, or they don't obey complete random matrix theory. So yeah, I'm not sure the terminology is super good, but the observation is that there's enhanced susceptibility, or at least in terms of scaling with the system size. And this can be detected much before you see full ergodicity. And so, I mean, in many ways, you could maybe think of this as kind of period doubling in classical systems, also being the precursor of becoming fully chaotic. Something similar is happening here. Okay, so to understand this, let's look at some more insightful quantity, maybe, which is just a spectral function. So let's define the spectral function, let's say f squared, which is just a Fourier transform of this infinite temperature correlation function. And this correlation function is just defined as the 2-point correlator between the lambda h and the lambda h at time t. Why am I defining this correlator between these two operators? Well, again, in the case of xxz, this is nothing but the correlator between the zz on the neighbors and zz on the neighbors evolved for time t. Well, because it's not so hard to see that basically the average fidelity susceptibility then would be nothing else but the integral of f of omega squared divided by omega squared, right? So if I know the behavior.
Can you talk a bit about what h of t is here? Do you like have a?
So the lambda h of t is nothing but the operator that I use to perturb the system evolved in the Heisenberg picture under the static Hamiltonian h. So h at parameter value lambda, and if we add an integrability breaking perturbation, also at fixed epsilon. And then, of course, we see that you can just express the susceptibility as the integral of the spectral function over omega squared. And again, I mean, you see that there's this small denominator because if f would be flat, if the spectral function would be flat at low frequencies, which it is for random matrix systems, well, then you see that you get some 1 over omega divergence of this integral, and 1 over omega divergence of this integral is nothing but scaling of the susceptibility with d, right? So now if we want to have scaling with d, well, scaling of the susceptibility, which is not d, but is faster than d, it basically means that we need to move a lot of spectral weight to low frequencies, right? Because I cannot get scaling of this typical or average chi with d squared if I don't move weight to low frequencies, because if I just assume it's a constant, well, then I just get d. So somehow as a function of L, as a function of system size, more weight needs to move to low frequencies. And so what I'm showing on the right is exactly the spectral function for the perturbation I was using before. And this is in the clean XXZ case, right? So for system size 12, 14, 16, 18, for a clean XXZ model. And so what we observe, this is a log scale. What we observe is basically there's some kind of diffusive behavior. So it's very hard to see, but if you would plot a 1 over square root omega here, it would actually asymptote this. And so diffusion in the XXZ model is now, I think, understood. But in contrast to random matrix systems, what we see is that there's a spectral gap. Suddenly the spectral weight goes to 0, right? And if I increase the system size, you see that the weight at low frequencies actually decreases. And that's roughly needed. Otherwise, in the clean XXZ model, I would get exponential susceptibility, right? So if I don't get exponential susceptibility, that means that I need no weight at low frequencies, right? So that's what we see. Now, if we switch on our perturbation epsilon, then what we see is suddenly a lot of weight appears at low frequencies. And if I were to do it for a larger system, I would even get more weight, right? And so as you can sort of, I hope, see, is that if I increase the system size, the spectral weight at low frequencies is exponentially increasing, right? Because this is a log scale. So every time I increase the system size, this exponentially increases. And it's this exponential increase of the spectral function at low frequencies that causes the susceptibility to grow with d squared and not with d. But this, at the same time, immediately implies that there is some exponentially slow dynamics in the system, right? Because I cannot have exponentially increasing spectral weight if this wouldn't be localized on frequencies which are also exponentially small, right? Because the integral of the spectral function needs to be fixed, right? It's conserved. And so if I generate more weight at low frequencies, it also needs to be pushed to a smaller frequency range. And so that basically means that from this, you can immediately see that some dynamics happens at exponentially late times. And what this dynamics is basically, in this case, is that you will thermalize to what you believe will be the unperturbed GGE kind of result for this observable. And then at exponentially long times, you will decay to the true thermal value. And so it's kind of pre-thermalization, if you want to call it like that. Okay, so this was the part on the clean system. Maybe if someone still has specific questions on that, now is a good time. No, okay, then I'll go on. So basically, I think what we learned from the clean system is that we can use this fidelity susceptibility to detect integrability, and this happens through some intermediate regime, where basically in this intermediate regime, a lot of weight moves to low frequencies, and this gives enhanced susceptibility. Okay, so now what happens in MBL systems? Well, MBL systems are very kind of special type of non-ergodic many-body quantum systems. We all know they have local emergent integrals of motion. There's no transport. They have area law entropy, logarithmic spreading of entanglement, in contrast to what happens in ergodic systems where they thermalize. There's volume law entropy, and you get ballistic entanglement spreading. And again, what we like to study is what happens to the ergodic system when we crank up the disorder and we go into this MBL system. And I'm gonna do exactly the same thing as I just described for the clean system. So let's take the XXZ model again, and let's add random fields in the Z direction, right? I'm gonna draw these random fields uniform between -1 and 1. And I just put the 1 over W, which is the disorder strength, in front of the XXZ model. If you like more, you can also scale everything with W, and then you get the standard thing. This is just slightly more convenient because, as I said, the fidelity susceptibility has units, and actually things look a bit nicer if you do it like this. So again, let's set expectations. So when the disorder W is small, right? So when this is small, then this term becomes very big. We can neglect roughly the disorder, apart from the fact that it does break integrability. And so what do we expect? Well, then the system should be ergodic, right? So we expect scaling of the fidelity susceptibility with D, the Hilbert space dimension. But as I said, because there's a 1/W in this problem, the fidelity susceptibility scales with W squared times D, right? That's the kind of the units. Okay, so that's our expectation on the ergodic side. So what is our expectation on the MBL side? Well, let's just pick W asymptotically large. So I can pick W asymptotically large, and I can probe, I didn't mention, so I can probe what I'm gonna probe here. So my d lambda h is gonna be just the local magnetization. So the local SZ on some side, call it side 0. And so you can just work out perturbatively what is the fidelity susceptibility in perturbation theory. It's not so complicated to do, and you get a 1/W squared, because if W would be infinite, then the thing is diagonal in Z. So if I'm probing Z, well, then I'm not changing the eigenstates, so the fidelity susceptibility is 0. And so to leading order, you get a 1/W squared. Then you get this expression with an energy denominator to the power 4, and this HXX is just the XX Hamiltonian, which does flip-flops between neighbors. And so what is now the problem? The problem already here you see is that if we were to take the disorder average of this chi, well, then this disorder average of chi would always diverge, because we have an energy denominator here to the power 4, right? And even in the unperturbed case, this energy denominator is nothing but the difference in magnetic field on the neighbors, right? But if I average this over all possible realizations of my disorder, well, then I'm dividing something by 1/x to the 4th, and I'm integrating it, so it's going to diverge rapidly, right? And this, you could say, is kind of a very trivial, well, not many-body resonance, but a very simple perturbative resonance. And you don't want to have this physics convolute the picture, right? So this is very simple to fix. The way to fix it is to not look in the mean, not look at the mean of chi, so the disordered average of the susceptibility, but you look at the typical susceptibility, right? And if you define the typical susceptibility as the exponential of the logarithmic average of the susceptibility, then these small denominators that you get in perturbation theory, they don't matter, right? They're all finite. And so you can just work out on a piece of paper, kind of combinatorially, what you would expect for the typical susceptibility at large disorder, and basically you can just show it decays like W to the -8/3. And so it's not W to the -2. So -2 you get from perturbation theory, but it actually decays faster. And the reason it decays faster is because they're only coupled. So you only get susceptibility by basically making Bell pairs between neighbors, right? Because those states are mixed and they become susceptible. But actually, if you would have a piece of a spin chain that would be fully polarized, right, where all the spins are up, well, then this XX Hamiltonian doesn't do anything, right? Because it just moves an upspin to another upspin. So basically, those terms are exactly 0. And so they will only contribute to higher orders in perturbation theory. And so if you take that into account, you actually see that the typical decays faster than W squared. Okay, so now that we know the expectation, namely that on the MBL side, we expect the typical susceptibility to basically decay to 0 as a power law of the disorder. And on the ETH side, we expect it to be exponential. Well, let's just look at the data, right? And so this is disorder, and this is the typical fidelity susceptibility. And so what I've done here is basically divided everything by D, right? And so at weak disorder, from say 0.1 to somewhere here, 0.5, what we see is that, so these are different system sizes, 12, 14, 16, 18. What we see is that if we divide everything by D, at small disorder W, all of the curves collapse, right? They're all on top of each other, which basically means the system there is exactly ergodic and it obeys ETH. It has exactly ETH scaling for the fidelity susceptibility in this regime. On the MBL side, well, on this rescaled plot, it's harder to see, but if we go to the unscaled plot, which is in this inset, actually on the MBL side, at large disorder, all the curves start to tend towards each other, and we can basically, at large disorder, exactly extract this power law slope. And there's some finite size corrections on this, and we can exactly compute these finite size corrections. And again, what we see is that this starting at disorder around 0.5, we start to see that all the curves start to slowly deviate from each other. And we start to see this enhancement in the susceptibility, right? And every time I increase the system size, I roughly get indeed an exponential increase in the susceptibility at some intermediate points. And so, as I said, this is ETH, and this is kind of this maximally chaotic regime where the fidelity susceptibility is exponentially higher than it was on the ETH side. And so, yeah, this now you could think, of course, as the MBL kind of critical point, right? Okay, so now again, as I said, we're gonna try to understand what's going on by again looking into the spectral function. And okay,
sorry,
yeah,
something must be missing, because if we take the disorder to 0, we recover an integrable model, and this shouldn't be
so
in
basically
the ETH regime.
Exactly. So that's why the plot is cut off at 0.1. So if you continue this plot, you're right. So if you go to 2-week disorder, then you also get integrable scaling again. That's completely correct. So yeah, you can if you want to look at the physics of going from ETH to MBL, you shouldn't go to 2-week disorders. Exactly.
So if you can bring this to a finish in about 5 minutes, because some people have to leave, then people can leave, and then we can keep discussing, if people who are interested can stay. But if you sort of...
Oh yeah, right. Okay, so basically we can look into the spectral function on the ETH side. And it's exactly the same as before. So we look into the 2-point correlator of the Z magnetization. And all the different curves show the spectral function for different values of the disorder in some appropriately rescaled frequency axis. And so what we see is that at low disorder, you just get diffusion. So this is 1/√ omega. And then if we crank up the disorder, we basically get a spectral function that starts to show some subdiffusive behavior. And it's tending towards a value which is kind of subdiffusion with an exponent 1. So it goes like 1/omega. And so what I've shown on this plot is basically the level spacing by these circles and the Taulus time by these squares. And so this is, how do I define the Taulus time? It's quote unquote the Taulus time. Basically, I'm just numerically defining it by computing the point of maximal curvature. So because we expect on this log-log scale that the spectral function is flat below the Taulus time and it's power law above. So I'm just extracting where is the curvature maximal. It's not really a good definition, but numerically it would be a way to determine this Taulus time. And so what we see is that this Taulus time is tending towards the level spacing, and indeed ergodicity would be broken when the Taulus energy becomes the level spacing. And so this shows the spectral function on the ETH side of the transition. So with increasing disorder, we go from here to slower dynamics here. If we now look at the spectral function on the MBL side, we exactly see that after this point where the Taulus time became the levels, Taulus energy became the level spacing, so where ergodicity got broken, the typical and the mean spectral function, they do not look the same anymore. So on the ETH side, the typical and the mean spectral function, they're exactly the same. On the MBL side, there's a big difference between the mean and the typical spectral function. The typical spectral function, they all for different disorders look identical, just that they're rescaled. In contrast, the mean spectral function basically shows decrease of this subdiffusion exponent on the MBL side of the transition. Okay, so given time, maybe for a second, I will skip this and come to the kind of, I think, crux of what I think our MBL data is showing, and I'm calling it the MBL paradox. So what have we observed? We have observed that there is slow subdiffusive transport with an exponent that tends to 1. And this observation is in agreement with a lot of numerical work by a lot of smart people before. There's also exponential enhancement of the susceptibility near the transition, right? And okay, now I'm gonna try to show you that those two are just one and the same thing. So again, recall that the susceptibility is nothing but the integral of the spectral function divided by omega squared, right? So if I put in that I have some behavior of the spectral function, which is subdiffusion with some this would be logarithmic subdiffusion, then of course, if I integrate chi and I get c over omega cubed, well, I exactly get that this integral diverges like c divided by the level spacing squared, which is exactly d squared, right? So having 1 over omega behavior of the spectral function or logarithmic spreading in space of the correlations is the same as saying that the fidelity susceptibility is exponentially enhanced near the critical point, right? So they are one and the same thing. This is also completely consistent with the notion that the Thouless time needs to become the Heisenberg time for ergodicity to be broken. So let's assume we have some hydrodynamic behavior where the correlation function c of t decays like t to the minus 1 over z, where z is some dynamical exponent. That means we get spreading in space because energy is conserved. So basically we get spreading in space like t to the 1 over z, or in other words, the Thouless energy is the length L of the system to the power minus z, right? So now what I want is that I'm gonna say that the MBL transition happens or ergodicity gets broken when the Thouless energy becomes of the order of the level spacing. Well, that immediately implies that if L to the minus Z needs to become 2 to the minus L, the level spacing, that Z needs to diverge, right? Z needs to become order L over log L. So if I just take the spectral function that goes with the subdiffusion, again, that would just basically mean that near the critical point or at the critical point, C should go, well, the spectral function should be 1 over omega with some correction, which is 1 over L, right? So again, that's the same. Saying that there's 1 over omega divergence of the spectral function is the same as saying that the fidelity susceptibility is enhanced. That's the same as saying that the Thouless time becomes the Heisenberg time at the critical point. But now we have a paradox because the total amount of spectral weight is fixed. That is, the integral of f of omega squared is fixed. It's 1/4 because the integral of f of omega is nothing but the norm of z, of the z operator, which is 1/4. So that basically means that if I have this spectral function, c divided by omega to the 1 minus z, that basically c, this constant c, times z has to be smaller than 1/4. That's just a mathematical identity that has to be true. So that means that this constant times the dynamical exponent has to be smaller than 1/4. But this constant c is a UV property of the system. It is determined at frequencies omega, which are of order 1, right? Because that's where the onset of this hydrodynamic behavior starts. So that constant c was determined in the UV. But if I have a local system, therefore C cannot depend on the system size L. But if this constant C cannot depend on the system size L, Z has to diverge like L over log L, well, then at some point, some rule, you're going to violate the fact that C times Z must be smaller than a quarter. And so numerically, we observe that basically C is 1 over the disorder strength, 1 over W. And so if you put C is 1 over W, you will immediately predict that the critical point shifts with L, like something order L divided by log L. And so that's exactly what we see. So that's exactly consistent with our observations. So just to go back, this constant C, if we have different values of the disorder W, this constant C is fixed. And if we increase the system size, so this constant C should be the, should be the slope of these curves. Well, with increasing system size, if anything happens for as finite system size effects, it is that this constant C is increasing with L, right? Not decreasing with L. But the point is that if you want the MBL transition to happen at a finite disorder, well, then it seems you require that C needs to be system size dependent, but it simply cannot because it violates locality. And so our proposition is that the fidelity susceptibility is peaked around the ergodicity breaking transition. It tends towards this maximal chaos bound, which is 4 to the L. We see 1 over omega subdiffusion that starts around W is 0.5, but the dynamics is so slow that basically there is not enough spectral weight that can actually give you the transition at a finite value of the disorder W, and it has to shift with L. And so there's something which I didn't discuss, that is that the fidelity susceptibility distribution, it also has anomalous tails on the MBL side, but that's maybe a story for another lecture. And so I'll stop here and then we can have some discussion after this.
Thank you, Dries. Well, I mean, there has already been some discussion, I guess. People who wish to leave, well, either have left or can leave now. We can also stop the recording if people are reluctant to talk because of it. And I think, you know, now people can freely ask